So I guess my talk today has a little bit less to do with oil and gas, but there are oil and gas applications such as survey, but really it's a talk about positioning, location, and navigation. And really, in terms of location, there's all kinds of things you can do with location. That's not really what trusted positioning does, but we actually get the location for you. And the location really is the core of the information. Once you have information, you have to communicate it, and then you do something with it. You have some service or application on top of that, whether that's your cell phone, your vehicle, or a survey type machine, or anything really, handheld survey. So in terms of location technologies, there's generally two categories. There's the wireless types of technologies, and in the next slide I'll get into the sensory-based technologies. But in terms of wireless technologies, I think we all know what GPS is. There's lots of GPS receivers in here, but there's multitudes of wireless. There's RF, there's ultra-wideband, there's all kinds of different areas. But really what these suffer from, they always face the conundrum of inaccuracy versus availability. So if you want a very, very accurate GPS receiver, you often have to give up in terms of availability. And if you want a very available solution, like your cell phone has, then often it's only accurate to say a few hundred meters. So in the case of, say, a survey under the trees, your GPS will probably fix itself here, but it's not going to be under 5-meter accuracy. In the case of, say, a machine control in a deep pit or underground, say downhole drilling, you're going to have no GPS or RF positioning here. So there's a couple different ways to get around this, but people have typically said, okay, well, forget about the preset infrastructures, let's sort of make our own. So Walmart tried to put in the RFID mandate, and that failed miserably, not because it didn't work, the technology was great, it's just because it was too expensive for all their suppliers to put in RFIDs on every single shirt or every single unit on a box. There's inertial sensors, and these have been around longer than GPS. The first space shuttles used inertial navigation. The problem here is that they're really big and bulky and expensive. So I'll talk a little bit about inertial sensor navigation, because probably most of you understand what GPS is, but inertial sensors are a little bit different. There's actually more inertial sensors right now in the world than there are people. There's probably more in this room right now than there are people. But where they came from were things like this, which would have been about the size of this screen, and they'd be used to navigate things like submarines, space shuttles back in the 60s. These are still undersea, they still work great, but of course they're very big and expensive. So there's new technology developed, fiber optical gyroscopes and ring laser gyroscopes were implemented. They're about maybe the size of that. So somewhat portable, but still the lowest cost units are about $5,000 to $10,000, and typically they're in about the $20,000 to $50,000 range. So this is sort of the status quo in today's market for inertial with GPS systems. There's MEMS technology. The previous talk was on nanotechnology, while MEMS is commercial right now. So MEMS technology is micro electromechanical systems, so 3 times larger than nano, officially, probably more, but. And these systems are quite small. These are in your phones today. They're used for things like screen rotation. They're in your tablets for drop protection, but they don't really use them for navigation. The reason why is because typical navigators are strapped to a unit. So you have a vehicle driving or a machine, so you strap them. And they had some uses for these in vehicles, but really if you're talking about very low cost, where these sensors are dollars instead of thousands of dollars, then you're looking at something like this, where it's not only a MEMS sensor, but it's highly deployable, portable, everything else usable. So trusted positioning, where we're working at, we're not developing any of the hardware. We don't develop GPS receivers, we don't develop inertial sensors, we don't develop magnetometers, but we put all of those together to get a more accurate, more reliable navigation, positioning, location solution at a cost that's deployable for things like precision agriculture, handheld mobile survey, mobile mapping, citizen mapping, these types of applications. So we're looking at a bill of material cost under 100. This unit here, the sensors were about $15. We're looking at delivering accuracy approaching the fog-based systems, so those $20,000 to $50,000 systems. The advantage with MEMS, of course, they don't suck all the power. They're very small. They're portable. And another usage of this would be cross-platform. So if it's a navigation system for one machine, it can be taken from that machine, put onto another machine in any orientation, and used seamlessly. So like I was saying, these are sort of your self-contained sensors, things like accelerometers, like in airbags, gyroscopes, like rollover detection gyroscopes, magnetometers, like in cell phones and your Garmin's, odometer, wheel-based systems. There's barometers, like in the Garmin e-Trex as well. There's all kinds of wireless infrastructures. GNSS is the general term which is Global Navigation Satellite Systems. GPS is just one of the several now. Wi-Fi, RFID, ultra-wideband, there's all kinds there. So really what we do is we take these existing infrastructures and sensors and we fuse them together to give a new navigation output that's more accurate and more reliable, and actually it's always available. So if you're looking at certain applications, like the ones I'll sort of focus on today because it's a little bit more relevant, would be machine control and survey. So machine control is sort of at one end of the spectrum, where you're looking at 10 millisecond latency between the time where a sensor senses something and it has to do something to the machine. Whereas at the other end of the spectrum, post-mission, would be the operator drives for an hour, 10 minutes, 2 days, whatever. They press a button and then it gives them the results. So it's operator driven. So I'll show you a couple results. I'll probably skip maybe one of them based on wherever I get, based on time. But the first one, I'll show you a walking handheld survey where it was sort of walking around the edges of buildings. The idea would be a survey type application. And the reason why we're walking around the outside of buildings is because that's where the GPS has trouble when you get close to an obstruction with the satellites. And you can see how the sensors perform. In this case, we were using the $15 sensors and a $25 consumer GPS. In the other one, we went actually to downtown Toronto. So we like to test in harsh conditions indoors. We can go indoors anywhere, but in terms of driving, we often have to go to a pretty big city. So Toronto is one of the best in the world. We've been to Taipei, Detroit, Houston, but Toronto represents the most difficult scenario we've seen. So I'm not expecting you to really see or get anything from this. All I'm saying is that we walked around our Calgary Technologies Inc. building, and the blue shows the GPS. The green is a reference solution, a $60,000 reference we carried in a backpack. And the red is our solution from holding it like this. So it's sort of meant to simulate a mobile type survey. So I'll show you a video that gives you more information on this. So again, the green is the reference, the blue is the GPS. And you can see in some cases there's no GPS here because of the trees. And then the GPS comes back. Here, we'll lose GPS up here, right here and here because of this apartment building here. We're actually walking behind it. So you can see there's sort of sporadic GPS. In some cases, the GPS is in error. Here, the GPS is off over here. We're somewhere in between the two solutions. So the point here is that GPS is sort of in and out, and it also has some errors. Whereas if you integrate it with sensors, it's a continuous available solution all the time. This is the Toronto Drive. I think this is, if you're familiar with Toronto, I think one of these is Yonge Street. It's downtown Toronto. And now what you can see is we're connecting the GPS dots with lines. And you can see that the GPS is really just a mess in downtown Toronto. As soon as you get into these urban type canyons, so this could be like a pit, the GPS is just awful. It's hundreds of meters off. So again, our solution is in red. The $60,000 reference is in green. And you'll see the GPS is actually off the screen many times. There's the occasional update, and now it's off the screen again. So there's no GPS here. So we're off by about a lane here. GPS is really noisy as well. Again, that's the availability versus accuracy problems. So here we're navigating without GPS. That's just the projection of a building in Google Earth. We didn't actually drive through there. You can see the lane changes of both. Turn. So I think you get the idea. I'll skip this one. It's really, this one is the same thing, but if we can do it in post-mission, so that was a real-time solution. In post-mission, the positioning results are about 2 to 3 times improved because we can actually not just do a forward process, but a backward process as well. So that would be like a survey-type application where the operator presses a button and it does a post-mission survey, and then he gets all the results of where he needs to redo or rerun the survey. These are some specs. We used a consumer-type GPS here, a U-Blocks. When the GPS was on, you can see that this GPS was giving us about 2.5 meters with the GPS only, and about 8 meters in the vertical. GPS is inherently much worse in vertical. So if you have applications like precision agriculture for boom control up and down, or earthworks where you need to raise a digger up and down, then vertical is a big problem. So this would be GPS only. And what we did is we actually removed the GPS and said, how do we do actually without the GPS with sensors only for different times? So operating for 10 seconds or about 1.7 meters, half a meter in vertical. Inherently, by the way we integrate, we're always better in vertical as opposed to GPS, so they complement each other nicely. For 30 seconds, it's still under 5 meters and 1 meter here. In this case, 10 minutes. This could be like a military type application where you're operating maybe near the border of a hostile country and you have to turn your GPS receiver off and just navigate with sensors only. So 10 minutes with nothing and using $70 sensors, we're at about 100 meters. So I brought a system here. I guess maybe I can show you in the break, but we have, we like to hook this up to fun little toys like tablets and development kits like phones running Windows, Android, Linux, these types of things. And this was our sensor system here, and we hooked that up by USB just to a Fujitsu tablet and ran it. There's all kinds of these MEMS sensors, like big names too. They come from Honeywell, Analog Devices, ST Micro. Just about any big semiconductor company now is making these MEMS. I guess it's pretty big at ACAMP too. Lots of GPS receivers. The in-town guys, the Novatel and Hemisphere, we support both of them. And lots of different ARM-based processors. So that's all I had. Thanks.